Hi, welcome to the materials session. I'm Steve Marshner, and I'll be the session chair for this session. Creating materials is one of those major content creation challenges in graphics, and there are many different approaches to it. And today we have two talks that are looking at two very different approaches to this problem. Remember during the talks that the Rocket chat channel is there. You can find it from the program, and please go ahead and post questions in the channel during the talk, and then we have them already queued up by the time we're ready to take questions afterwards. So the first talk is called Guided Fine-Tuning for Large-Scale Material Transfer. The authors are Valentin Deschaintre, George Drettakis, and Adrien Bousseau, and Valentin will be giving the talk. So Valentin, take it away.
Hello, thanks for the introduction. I am Valentin, and I'm going to present our work on guided fine-tuning for large-scale material transfer. Let me first explain our motivation. On the left here, you have the Rothschild Villa, which is close to Nice and the lab I did my thesis in. While visiting this villa, I found many pretty surfaces, such as this mosaic here, or this one, or this tiling. At this point, I had been working on material acquisition for a while, so I was curious, how can I reproduce these surfaces in a virtual environment? Essentially, I wanted to extract the material parameters. In this case, the normal, the diffuse, the roughness, which drives the shininess, and the specular parameters. And all of these from a picture of a surface of arbitrary scale, up to multiple meters, of arbitrary aspect ratio, and potentially taken outdoor. Now, historically, many methods were proposed for precise material acquisition. They are usually based on specialized devices and control lighting with multiple measurement. And this doesn't really fit our on-site catcher problem. And furthermore, these methods are not designed for large-scale surfaces acquisition. Simpler methods have been proposed, but they still require many pictures from different angles or rely on strong priors such as material self-repetitivity. In the past couple of years, multiple methods, including ours, were proposed, leveraging deep learning to extract material information from one or a few flash pictures. The general idea is to use a flash picture as input to a network trained specifically to output material parameters. While the flash in the picture does indeed bring important information to these methods about the material properties they are trying to capture, it also comes with two drawbacks. The first one is that it intrinsically introduces a strong light variation over the input, which means that to fully benefit from the flash cues, the deep network needs to process the full image in one go. And well, given the training time and memory footprint of networks, there is a limit to the image input definition you can handle. But even if you had NVIDIA's processing power, for example, there is a second limitation. And it is the scale. When using a flash, you need to stay rather close to the surface you want to capture, because you want to make sure that the effect of the flash is clearly visible on the surface, and this limits the possible scale of acquisition. So here is a mosaic I want to acquire, and here is the approximate scale that flash methods can handle. So either I carefully take many pictures of the surface, or maybe I should consider not using a flash. In 2017, Lee and colleagues proposed a deep learning-based method for no flash acquisition. But because of the lacking flash information, they needed to train one network per material type, for example wood, metal, or plastic. And they inferred constant roughness and specularity over the acquired material. So on one end, we have a large-scale picture without a flash, which is missing specular information, and on the other hand, we have small-scale flash pictures from which we know how to extract material parameters. So the question is, could we combine those and transfer the information from the small scale to the full picture? So this becomes an information transfer problem. Different methods use patch-based synthesis approaches, which are akin to image analogies for style transfer or material transfer. But those require that a correspondence for each patch of the target image can be found in the example image, which is often not the case in our problem. Deep learning methods have been proposed, such as this work by Gattis and colleagues and Huang and Belongi. But these methods focus more on global statistics transfer and do not capture well local details. Recent methods combine both approaches, the dense patch correspondences with deep learning image transformation. But once again, this kind of approach requires all of the information to be available in the exemplar image. We propose a transfer method which does not require explicit correspondences. We do this by specializing a network to map between the large-scale image color and texture and the example material parameters. A related idea to shortly specialize a network for the processing of a specific image also appears in a new work by Texler and colleagues that will be presented at SIGGRAPH later this summer. So let's now discuss in more detail how we combine the available information from the small scale to the large scale. As I briefly mentioned, we want to specialize a network to process this large-scale image on the bottom left. And we propose to use the small-scale exemplar as training data to fine-tune our network. And once the network is fine-tuned, after a few minutes, we can process our large-scale HD image. Now, in more details, I will first discuss what our method inputs are and how we process them. I will then describe our network fine-tuning approach. And finally, how we prevent the fine-tuning to overfit. So first, our acquisition process. Our inputs are a large-scale picture of arbitrary resolution and aspect ratio with approximately constant illumination. We also provide an exemplar material. In this case, the exemplar comes from a close-up flash picture that we processed with our 2018 single image method. From this, we retrieve material with the same resolution as the input's large-scale image. Now, because our method simply requires mostly uniform lighting in the large-scale input and some material exemplar, we can also use online textures and a material exemplar from an existing SVB-IDF library. This allows to create physically based material from online texture, allowing for some creative freedom. To be able to process HD images with arbitrary aspect ratio, we split the large image in 512 by 512 tiles, which can then be processed individually. This process is possible because the lighting is approximately constant over our entire input. So each tile is processed individually through the network and stitched back together to get the final result. But if we stitch the result using a simple average of overlapping tile, we get unpleasant seams, as you can see here, for example. Instead, we weight each tile by a Gaussian function which gives more importance to the center of each tile, which leads to less discontinuity in the results, as you can see on the right. So we have each tile now, and we want to process them through the network while still taking the exemplar properties into account. We start by training the network we proposed in 2018, but this time on 512 by 512 no-flash pictures. And we train it to output SVB-IDF parameters in the form of normal, diffuse, roughness, and specular maps. To pre-train the network, we use synthetic data. At each training step, we randomly select SVB-IDF, which we randomly crop and blend to augment the variety. And we finally render them with a random directional lighting to create the training input images. Once trained, the network does a reasonable job inferring the normal and diffuse albedo, but it has little cues on roughness and specularity. So we have our trained network and our material exemplar. We want to infuse the pre-trained network with the information that is available in the material exemplar. And to do so, we propose to fine-tune the network. The fine-tuning takes a few minutes, which represents about 1,000 fine-tuning steps. And at each step, we render training input images of the material exemplar, which we use as inputs using the exemplar material maps as ground truths to fine-tune the network. After a couple minutes, we have our fine-tuned network. We can now use it to process each individual tile and get the material maps we're interested in, while still taking into account our exemplar properties. Here, we compare the results without fine-tuning on the top and with fine-tuning in the bottom. As you can see, the roughness properties of the brick exemplar were transferred, leading the bricks in the results to be shinier than the white paint. So while our fine-tuning can be used directly as such, if the exemplars are too simple, the network can overfit. Here, the exemplars are mostly constant materials, and if you use the fine-tuning directly with these, the network will overfit to an average mix of the exemplar, as you can see on the right. We propose a new augmentation system to avoid this. We create random masks based on thresholded low-frequency Perlin noise, allowing to create random spatial mix of the exemplars, which still preserve their individual properties, leading to better spatial distribution in the results. As you can see here in the zoomed specular and roughness maps. Let's now see some results. First, the mosaic I was mentioning in the beginning. Here, the high resolution helps to distinguish each detail of it. In this result, we can see that the shiny behavior of the orange square, which is visible in the exemplar on the bottom left here, is well propagated to the entire material. So, back to our villa. We now have a virtual representation of the surfaces I mentioned in the beginning. Here we have another example of the creative design workflow I described earlier. As I mentioned, this pipeline allows to easily apply our method to a large variety of surfaces, and to quickly transform existing textures to PBR materials. To illustrate the variety of materials acquired or created using our method, in this video we show renderings of different surfaces with strongly spatially varying materials. This video also illustrates the variety of aspect ratio we worked with. We could process tiles, metals, stones, mosaics, and more on surfaces spanning from a few dozen square centimeters to multiple square meters, with resolutions up to 2K by 4K. The results visible in this video are all available in our supplemental materials. We compare our results with previous work on material acquisition and style transfer. First, we compare our method without exemplar on the top, and our method with an exemplar from our method from 2018 on the bottom. We can see that we are more accurate, especially in the roughness parameter. We also compare on the same material between our 2018 method with flash this time on the top row, and our method with ground truth exemplar on the bottom row. And we can see that with good exemplar, our method improves significantly. This means that our method benefits from the quality of the provided exemplars. We now compare two style transfer methods.
Here with Adrien on the top row, which is a global style transfer method I mentioned earlier. And we see that for each parameter map, the general style is reasonable, but the local information is not well transferred, which is especially visible in the normal maps here on the left. Here we compare to the methods that are based on image analogies. In this example, we used a modern implementation of image analogies from Fisher and colleagues. And as you can see, the image analogy approach does a much better job than Adrien, but it doesn't work so well, despite a good exemplar, because parts of the large-scale image are not covered in the exemplar, which is likely to happen in our scenario. In this case, it's particularly visible with artifacts that appear in the normal maps. Before concluding, I would like to show some example of the control that is available to the users by changing the exemplars. I will use this golden crane example. Here, we replace a shiny gold by a rougher gold exemplar. This results in a rougher output, as you can also see in the renderings. In the second example, we change the specularity of the exemplar to remove the golden aspect, which is particularly visible in the specular output map. Finally, we add an outlier exemplar to test the robustness of our approach with a red diffuse material that you can see here in the bottom left. The effect can especially be seen with the red tint that is given to the diffuse albedo, but we can see that the overall results stay coherent. But of course, some limitations remain. The first limitation is in the lighting condition. If we have strong lighting variation over the surface, our method doesn't manage to compensate for it, as you can see in the result in the center and the renderings on the right. Our second limitation happens in the case where two different materials look similar in the large-scale image. Here, the network propagates the small manhole properties to the dark part of the pavement. To conclude, we developed a method that is able to reconstruct HD, large-scale, spatially varying material parameters. We introduce the possibility of high-level control over the results, and facilitate the transformation of online textures to physically based materials. Most importantly, we enable all these applications by simply fine-tuning a deep network to infuse it with information from a user-provided exemplar. So, with this, I thank you for your attention. Our code, data, and supplemental materials are available on this link. I would be happy to answer any questions.
All right, thank you for that nice talk. We have plenty of time for questions here, and so I will invite people to please submit some in the Rocket Chat channel. And since I don't see any there yet, let me ask a couple questions of my own. So one question, so you have a material that you photographed at the large scale, and then there's a collection of exemplars you supply. And you can kind of control the appearance by changing what those exemplars are. One question is, how important is it that they actually resemble the real material? Or does it work better if they resemble the real material, or are you free to just sort of play with whatever you put in to get different kinds of effects?
It's better if it generally looks the same way in terms of rough color and texture. You can have dramatically different specular behavior, I think, without completely breaking the method, I think. Yeah.
Okay. Another kind of related question is do you have like an intuitive sense of to what extent it mainly cues on the color that's in the image, in the large scale image, and to what extent it is cueing on, other texture or shape cues when it decides which mix of, well, I don't know, it's not really mixing them explicitly, but when it generates the SVBRDF.
Yeah, we've been trying to experiment with this and figure out something with a different texture but the same color and so on. But so that works with different texture but the same color, but different color and same texture will not work. Color has a strong role in the driving for sure. Yeah, finding two, we did not manage to find exactly two materials that would have the exact same color but slightly different texture with a large scale. Yeah.
Yeah, I can imagine it's hard to find the real test cases because these things do. I mean, one of the things that makes this work is that those things do tend to vary together.
Yes.
So I see we have a question coming, so I'll ask a quick one. When you are merging the tiles, you do some blending.
Yes.
And so when you do that blending, you are blending between different collections of material parameters, which I suppose could be potentially rather different. And have you thought about the implications of blending these kind of nonlinear material parameters, such as normal maps and things like that, or has this not really ever seemed to be an issue?
The normal map we blend carefully as these are vectors essentially. Other blending, we don't really have so much difference between the different tiles because the entire network is how to say really specialized on the same kind of parameters for the same color or material. Mm-hmm. So it will output tiles that are already almost coherent. So when we blend them, we simply make sure that the center of the tile has more weight in the final appearance.
Right.
So because we just want to avoid the seams. We have not seen major difference in the values themselves.
Right. Okay, that makes sense. And I guess since it's convolutional, it's expected to, once it's toward the interior of these things, it's expected to behave similarly.
Yeah.
So we have a question from Tommy Bobikor. How flat is the input expected? Which I'm guessing might be asking sort of how much relief do you really tolerate well?
So because we use a cooktolerance model, and normal map, we don't really handle self-occlusion or explicit 3D structures. So it has to be relatively flat. That being said, we were able to treat stones of reasonable size on walls and such things. Mm-hmm. I suspect that you can have slightly bended inputs, large-scale input. It would not matter much to the network. If you want to treat more 3D objects with that, I don't see why it would not be possible. It would simply require to train the network explicitly to recover SVBRDF from a 3D object, and then probably the fine-tuning would be done by rendering on small shapes the different exemplars.
Mm-hmm. That makes sense. One more question. It's interesting that you had an example in the paper that showed that if you include an exemplar that doesn't really match the material, when you already have exemplars that match pretty well, it does still affect the output. Have you thought about why this is?
Yes, I believe that the network in this case will try to find, is essentially told there is something like this. It's likely that you will see something like this. And so it will, I think, bring some kind of the average of this material a bit everywhere because it doesn't really know where to put it.
Mm-hmm. Yeah, that makes sense. Okay, and one more question from the chat, which will be our last one, from Guprit Singh. The training time is super long, and do you have any ideas about what components are making the learning difficult? And is it possible that maybe a different representation, like a bilateral grid, could help reduce it?
I'm not sure what you mean by the training time is super long. If we could explicit which part. The pre-training takes 7 days.
I think that's the part that he's talking about.
Okay. I find it to be in general similar to what previous method had, just it's on larger resolution, so it takes a bit more time. I'm sure we could accelerate it by simplifying the network. There is the fact that we use in this network inverse rendering, which takes some time. Mm-hmm. So yeah, I'm sure this network can be optimized for more production purposes. But this pre-training is done only once. You really don't have to do it more. Then you have between 2 and 5 minutes of post-training, depending on how much you want the exemplar to influence the output.
Right. Great. All right. Thank you. These are good talk and good answers to the questions, and it's a really interesting method. So moving on to the next paper in the session, it's entitled Photorealistic Material Editing Through Direct Image Manipulation. The authors are Károly, Zsolnai-Fehér, Peter Wonka, and Michael Wimmer. And Károly has done the talk, and so let's go to that video now.
In a previous paper, our goal was to populate this scene with over 100 materials with a learning-based technique and create a beautiful planet with rich vegetation. The results looked like this. One of the key elements to accomplish this was to use a neural renderer, or in other words, a decoder network that you see here, which took a material's shader description as an input and predicted its appearance, thereby replacing the renderer we used in the project. It had its own limitations. For instance, it was limited to this scene with a fixed lighting setup, and only the material properties were subject to change. But, in return, it mimicked the global illumination renderer rapidly and faithfully. And in this new work, our goal was to take a different vantage point and help artists with general image processing knowledge to perform material synthesis. Now, this sounds a little nebulous, so let me explain. One of the key ideas is to achieve this with a system that is meant to take images from its own renderer, like the ones you see here. But, of course, we produce these ourselves, so obviously we know how to do it, so this is not very useful yet. However, the twist is that we only start out with an image of this source material and then load it into a raster image editing program like Photoshop and edit it to our liking and just pretend that this is achievable with our renderer. As you see, many of these target images in the middle are results of poorly executed edits. For instance, the stitched specular highlight in the first example isn't very well done, and neither is the background of the gold target image in the middle. However, in the next step, our method proceeds to find a photorealistic material description that, when rendered, resembles this target image and works well even in the presence of these poorly executed edits. The whole process executes in 20 seconds. To produce a mathematical formulation for this problem, we started with this. We have an input image T and edit it to our liking to get the target image T with a tilde. Now we are looking for a shader parameter set X that, when rendered with the phi operator, approximates the edited image. The constraint below stipulates that we would remain within the physical boundaries for each parameter, for instance, albedos between 0 and 1, proper indices of refraction, and so on. So, how do we deal with phi? We use the previously mentioned neural renderer to implement it, otherwise this optimization process would take 25 hours. Later, we made an equivalent, unconstrained reformulation of this problem to be able to accommodate a greater set of optimizers. This all sounds great on paper and works reasonably well for materials that can be exactly matched with this shader, like this one. This optimizer-based solution can achieve it reasonably well. But, unfortunately, for more challenging cases, as you see the target image on the lower right, the optimizer's output leaves much to be desired. Note again that the result on the upper right is achievable with the shader, while the lower right is a challenging, imaginary material that we are trying to achieve. The fact that this is quite difficult is not a surprise because we have a nonlinear and non-convex optimization problem, which is also high-dimensional. So, this optimization solution is also quite slow, but it can start inching towards the target image. As an alternative solution, we also developed something that we call an inversion network. This addresses the adjoint problem of neural rendering, or, in other words, we show it the edited input image and out comes the shader that would produce this image. We have trained 9 different neural network architectures for this problem, which sounds great. So, how well did it work? Well, we found out that none of them are really satisfactory for more difficult edits because all of the target images are far outside of the training domain. We just cannot prepare the networks to be able to handle the rich variety of edits that come from the artists. However, some of them are, one could say, almost usable. For instance, number 1 and 5 are not complete failures. And note that these solutions are provided instantly. So, we have 2 techniques, none of them are perfect for our task, a fast and approximate solution with the inversion networks, and a slower optimizer that can slowly inch towards the target image. Our key insight here is that we can produce a hybrid method that fuses the 2 solutions together. The workflow goes as follows. We take an image of the initial source material and edit it to our liking to get this target image. Then we create a coarse prediction with a selection of inversion networks to initialize the optimizer with the prediction of one of these neural networks. Preferably a good one, so the optimizer can start out from a reasonable initial guess. So, how well does this hybrid method work? I'll show you in a moment. Here, we start out with an achievable target image and then try 2 challenging image editing operations. This image can be reproduced perfectly as long as the inversion process works reliably. Unfortunately, as you see here, this is not the case. In the first row, using the optimizer and the inversion networks separately, we get results that fail to capture the specular highlight properly. In the second row, we have deleted the specular highlight on the target image on the right and replaced it with a completely different one. I like to call this the Franken BRDF, and it would be amazing if we could do this, but unfortunately, both the optimizer and the inversion networks flounder. Another thing that would be really nice to do is deleting the specular highlight and filling the image via image inpainting. This kind of works with the optimizer, but you'll see in a moment that it's not nearly as good as it could be. And now, if you look carefully, you see that our hybrid method outperforms both of these techniques in each of the 3 cases. In the paper, we report results on a dozen more cases as well. We make an even stronger claim in the paper where we say that these results are close to the global optimum. You see the results of this hybrid method if you look at the intersection of Nelder-Mead and NN, they are highlighted with the red ellipses. The records in the table show the RMS errors and are subject to minimization. With this, you see that this goes neck and neck with the global optimizer, which is highlighted with green. In summary, our technique runs in approximately 20 seconds, works for specular highlight editing, image blending, stitching, inpainting, and more. The proposed method is robust, works even in the presence of poorly edited images, and can be easily deployed in already existing rendering systems and allows for rapid material prototyping for artists working in the industry. It is also independent of the underlying principal shader, so you can also add your own and expect it to work well as long as the neural renderer works reliably. A key limitation of the work is that it only takes images in this canonical scene with a carved sphere material sample, but we conjecture that it can be extended to be more general and propose a way to do it in the paper. Make sure to have a closer look if you're interested. The teaser image of this paper is showcased in the 2020 Computer Graphics Forum cover page. The whole thing is also quite simple to implement, and we provide the source code, pre-trained networks on our website, and all of them are under a permissive license. Thank you so much for watching this, and a big thanks to Peter Wonka and Michael Wimmer for advising this work.
All right, thank you for that really nice presentation. So we have time for some questions, and I encourage viewers to please post questions in the Rocket Chat channel, which you can get from the program as usual. In the meantime, I have a couple of questions of my own. So one question, it's interesting that you phrase this not as the artist provides a totally random image, but the artist provides an image that was edited to change the appearance. And this suggests that you could imagine, if this works well for small changes, but not as well for large changes, that it would be more effective if you did it sort of continuously in a number of very small changes that bring the image from the original to the edited one. And I'm curious if you've thought about this kind of continuous way of doing it, or whether you have observations about whether small changes are much easier than large changes.
Okay, depending on how you define a small or large change, we have a number of examples in the paper. If you think about small or large changes in a sense of like pixel footprint, like changing a specular highlight, we have a lot of examples on that. But for instance, there is this Franken BRDF example as well, where we touch up the image at several points. So a big part of the image has been changed, and it still seems to work well. And regarding the continuous part, we have thought of that. I think we have a good design here in a sense that in an artistic workflow, it often happens that you try things in Photoshop, you have different sliders, and you don't know how much you would like to blur something, or how the albedo changes, how pronounced they should be. And you would like to change things around, move the sliders around, and then in the end, you see that, okay, I like this one. And we support this kind of workflow. And we discuss in the paper that what you can also do is that there is a variant of this that works for image sequences. So you can imagine an image sequence as not necessarily a video or anything like that, but like a Photoshop workflow, where you start out with a little blur, you start playing with the parameters, and you find the right one. And roughly in these cases, you can get interactive results, something like 1.5 seconds per frame or something like that. So you can imagine a UI where you change these sliders around, and every second or every other second, you see the updated result of what can be achieved with a shader.
Yeah, that sounds like that would be a really usable workflow. So we have some questions coming in. So one from Murat Kurt, can you represent anisotropic materials with your framework?
The way we try to pitch this method is that it is kind of tailored to the shader that we have at hand. So I know that our shader can do a lot of things with specular highlights, and we play with the images that way. However, it is also agnostic of the underlying shader. So this was a general purpose principal shader that can create most of the materials you would want in a general use case. But we also discuss in the paper that you could likely plug in some very specialized shaders like thin film interference, things like that. And as long as the edits that you make to that you apply to the image resemble the thing that you would like to get, I think it should work.
Okay, and you just would have to retrain those networks based on the new model.
Yes, exactly.
But you're right that as the overall thing is the overall principle is all general. So there's another question coming, it looks like, but here's a quick one in the interim. So you have a system where you run 9 different variants of a network and then take the best of the outputs. I'm curious if you have thoughts about how that differs from just training a larger network that maybe has a, that might be able to essentially implement a 9-way choice at the last layer.
I can imagine that you could have one really nice neural network, like something like a UNet or something that works better, and you can use that one neural network, and you don't have to do this best of 9 thing. However, we are trying to make a point that there are cases where all of the interesting cases, so you train the neural network within the boundaries of the shader. So you cannot have albedos larger than 1 and things like that. However, if you get an input image from the artist, that may be something that's entirely non-physical. And what you are looking for is the closest match to the image that is still achievable with the shader. And maybe you can get closer to that if you have one powerful neural network, but still, our experience is that there can be so many edits that you can apply to these images that it's hard to train neural networks for that. And that's one of the points that we are also trying to make, that there are cases where you have many approximate solutions, and how can you find the best one and still combine with an optimizer to get something even better.
Right. Yeah, and starting with a number of different starting points to find when you're searching a very non-convex space makes sense. Mm-hmm. A related question from Guprit Singh. You mentioned that your results are close to global minima, but the demonstrated results, like the image in painting, are perceptually far from the target. Do you have any reasons for that?
Mm-hmm. Sure. I think that's a very good remark that comes up very often also in our discussions. So the input images that are created by the artist, these are typically not achievable. So when we are talking about optima, it usually means as close as we can get to that image. But these are often very non-physical images. So it can happen that, sure, it's not exactly the same as the output image, but it's as close as you can get, given the constraints of the shader.
Do you have any way to evaluate whether you have found a global minimum or whether there's another minimum somewhere far away that might be better?
It is possible. I would say in this case, unlikely. We have a very, I think on the last page or the second to last page, we have a big table where we compare this against the global minimizer, which we have given a generous allowance to run for a long time. And the results often match that. I think in almost every case are matching or very close to that. Obviously, this is not a mathematically proven thing, but we try to show that on many practical cases, this is close to the global minimum.
Right, right. Which is typically the best guarantee you can give for a non-convex problem like this. All right. Well, thanks very much. And with that, we'll bring this session to a close. And we have a few minutes before the town hall, and you'll all head over there.
Thank you very much.